Hello, my awesome AP Chemers. Today we're going to start chapter 14, which talks about chemical kinetics. So chemical kinetics have to do with reaction rates, how fast a reaction occurs. So as always, we have our learning objectives, which are really important. Make sure that you read over those, especially before a test or before the exam. We have a couple of exclusion statements as well. These are things that are out of the AP exam. So let's start with like a little bit of an introduction of what are reaction rates and what do they mean. So the rate of a chemical reaction, the rate of anything, like let's say you are driving to school and I ask you, what is your rate? Well, it's usually the change in something per change in time. So for, your speed driving to school, it would be change in distance over time. In a chemical reaction, what changes is the species, the concentration of your substances. So as you start out, you have a lot of reactants. When time goes by, they get used up, so your concentration of the reactants decrease. Or you can think about the products. You start with no products, and over time, the concentration of the products increase. So in a chemical reaction, the rate of a chemical reaction will be the change in concentration over time. Let's write that down. So, change in concentration over change in time. And so we say change in concentration over change in time, like that. So at a given temperature, all reactions should have a definite rate. And we say that because the temperature will actually change the rate of our reaction. But at a given temperature, each reaction should have a set rate. So let's take a look at the decomposition of a hydrogen peroxide here. It decomposes to water and oxygen, of course. And so you see the time here, and hydrogen peroxide is our reactant, so you start with a pretty high concentration relatively, and as time goes by, it decreases. It gets used up, turns into the products. Oxygen, which is one of the products, starts out at 0 because you don't have any products to begin with, but then its concentration increases. And you see that from the data table. You also see it from the graph here. So if we graph concentration versus time, you will see that your hydrogen peroxide, which is in red here, starts high and decreases as time goes by. And then the product, which is the oxygen here, starts at 0 and then it increases over time. So at time equals 0, you start out with all reactants and 0 products, which makes sense. Let's look at from time equals 0 to time equals 200 minutes, what happens to the rate. So let's say we want to determine the rate from 0 to 200 minutes. So we'd say, well, the rate is equal to the change in concentration over time. And we want to find the rate with respect to the hydrogen peroxide here. So we're going to look at the change in the concentration of the hydrogen peroxide from 0 to 200. So we're going to say the rate is equal to the change in the concentration of the H2O2. Now, you have to look at it whether it's a reactant or a product. If it's a product, you leave it as is with a positive sign because it's forming. If it's a reactant, you put a negative sign in front of it because it's being used up. So then we're going to say it is equal to negative, and change in anything is always final minus initial. So final is my 200, so 0.0162 molar minus my initial is this right here, 0.0200 molar, over change in time, again final minus initial, so 200 minutes minus 0 minutes. Again, if it's a reactant, you put a negative right here because then it's going to give you what the rate is as an absolute value, not as a negative value. Since the hydrogen peroxide is a reactant. So in front of reactants, you put a negative. In front of products, you don't do anything. So the rate ends up being 1.9 times 10 to the 5th. And the units for that are going to be molar per minute. It's usually concentration per time. So that means every minute we use up this much hydrogen peroxide. Okay, let's look at from 200 to 400 minutes, and we're going to look at it with respect to the hydrogen peroxide, which is a reactant, and then also with respect to the oxygen, which is a product. So let's start with the hydrogen peroxide. So we're going to say the rate is equal to negative change in the H2O2 concentration over time, just like we did earlier. So negative, and then for 400 to 200, so 400 is 0.0131 molar minus the 200 is 0.0162 molar, divided by change in time, final minus initial, 400 minutes minus 200 minutes, and we'll calculate that. This gives us 1.55 times 10 to the negative 5th molar per minute. Now let's do it with respect to the oxygen. So the rate is going to be equal to the change in concentration of the oxygen over change in time. We don't put a negative there because the oxygen is, we say appearing or forming. 400 for oxygen is 0.0034 molar minus 0.0019 molar at 200 minutes. And this gives us 7.5 times 10 to the negative 6 molar per minute. So we calculated the rate in terms of, we call it the disappearance of hydrogen peroxide and the appearance of the oxygen. I don't necessarily love these words because, you know, our reactants don't disappear and our products don't appear, right? They form or they get used up or something like, or we react. But that's the terminology that we normally use with kinetics. So you'll see that for the same time frame, the rate of the appearance of the oxygen is different from the rate of the disappearance of the hydrogen peroxide. And if you look closely at the numbers, this number looks like it's double this number. So why do you think that is? Let's look at the reaction here. Why do you think this is? Can you guess? We're comparing hydrogen peroxide, that being used up, the rate of this being used up to the rate of this forming. You can see from the molar ratio here that for every 2 moles of hydrogen peroxide that get used up, we form 1 mole of oxygen. So the formation of the oxygen should be half the using up of the hydrogen peroxide because it's a 2-to-1 ratio. And that's what we see right here, that the formation of the oxygen is about half the rate of the disappearance of the hydrogen peroxide. Let's write that down here. It's a different color. Okay, so we're going to look at these here and we'll say the rate of appearance of O2 is half the rate of disappearance of the hydrogen peroxide. And again, we can see that from our molar ratio there in the equation. The rate can be expressed in terms of, like we just said, the disappearance of the reactants or the appearance of the products. And we can relate them based on the molar ratio like we just saw. So in this case, I'm going to rewrite the equation here so we can see it. We can see that it's a 2-to-1 ratio here. So what we do is we can say rate is equal to, if we are going to compare between the two, like if we have the rate of one and we're trying to find the rate of the other, what we do is we put, like we said, negative for the reactants, and we put 1 over the coefficient for each of the substances. So this one is half change in the H2O2 over delta T is equal to, for the H2O, this is a product, so we use positive, and we do 1 over the coefficient, so half change in the concentration of the H2O over time. That is also equal to, this is a product, so we use positive, and we do 1 over the coefficient. 1 over 1 is just 1. The change in the concentration of O2 over delta T. Now, we only do that where it's 1 over the coefficient if we're relating one substance to the other. So what we're saying here is the change in the O2 is equal to half the change in the H2O, or negative half the change in the H2O2, just from this right here. So you can just look at the equation and be able to tell that, or if you want to express it mathematically, this is how you would express it in an equation, relating all of them to each other.